Hello everyone, and welcome to this lecture on remote sensing and archaeology, an introduction. I'm Alex Turner. The topics we'll cover today on remote sensing are: what is remote sensing? A very fundamental question. The definitions of remote sensing, there's more than one. Remote sensing techniques, survey scale. We'll have a look at satellite imagery and LiDAR, and briefly aerial photography, because you're going to cover that in some of the other sessions. And then we'll look at UAV and geophysics. And for this lecture, I'm going to use two sites. For the overview of methods, I'm going to use the World Heritage Site of Avebury in Wiltshire. And for the detailed case study, I'm going to draw on the archaeology work at Corbridge in Northumberland, particularly around the Roman site. Okay, so what is remote sensing? Some archaeologists define it as the technique of obtaining information about objects through the analysis of data collected by sensors, cameras, scanners, imaging radar systems, etc., using, and this is the key point, spaceborne and airborne instruments. So this definition very much revolves around the remote sensing being related to anything that's spaceborne or airborne. It doesn't include ground-based techniques. Other archaeologists believe that any non-invasive approach to viewing the buried and nominally invisible evidence of past activity should be included within the term remote sensing. Any method that allows the observation of the buried evidence without impacting the surviving stratigraphy is allowed with this definition of remote sensing. So here, what we're looking at is a definition that allows for not only the spaceborne and airborne instruments, but also the ground-based instruments for things like geophysics. If we want to take both of those ideas and create a sort of summary of the idea of remote sensing in archaeology, then I guess we end up with this phrase, which is the science of identifying, observing, interpreting, and measuring objects or surfaces without coming into direct contact with them. So the thing here is being able to measure things without being in direct contact with them. Okay, so these are the remote sensing techniques we're going to consider during today's lecture. They are the most commonly applied techniques. There are a few others that we could add in, but this is an overview, an introduction. So we're going to look at satellite imagery. So basically imagery derived from satellites. And we'll look at some historical and some modern examples of this. We're going to look at LiDAR, which is airborne laser scanning, and is commonly used by the Environment Agency in this country. We're going to look at aerial photography. We'll cover this briefly, but it's important that you understand how this fits in with the other remote sensing techniques. We're going to look at UAVs, or unmanned aerial vehicles. This is an increasingly popular way of capturing aerial imagery using drone technology. And finally, we're going to look at some geophysics. So we're going to look at some ground-based capture of archaeological data. Before we can decide which technique to use for any particular project, we need to think about the scale of the project that we're dealing with. So here we've got a series of extracts from Ordnance Survey maps, which give you some idea of the level of detail that you get at various scales. We have what we call the macro scales, which are the things like 1 to 1 million, down to perhaps 1 to 50,000. And we have the micro scales, which are 1 to 25,000, and more detailed 1 to 10,000 and 1 to 2,500. The level of detail that you decide to employ for any project will depend very much on the geographical area that you're looking at. So let's think about macro scales. If you were doing something at a macro scale, you'll be thinking about something like a part of a country at 1 to 1 million. But this might be quite good if you're looking at patterns of movement or trade. 1 to 250,000, This is sort of the county-based scale of looking at data. Again, this might be useful if you're doing a survey which involves a lot of sites spread around the county, for instance. And then we move down to sort of the village or the small town level, which is at 1 to 50,000. When we come to looking at the detail of sites, we need to be thinking about micro scales. So this is 1 to 25,000, 1 to 10,000, 1 to 2,500. These are the sorts of scales of map that you will be able to download from Digimap. You could have things that are even more detailed than 1 to 2,500, but as we will see when we look at the various methods, not a lot of methods are suitable for anything that greater than perhaps 1 to 2,500. So, satellite imaging. Knowing the scale at which you're going to actually produce the project finally is very important when it comes to deciding what type of image to use. So here we've got an example of an image taken from the International Space Station of southern Britain. And you can see here its relationship with northern continental Europe. This would be a very good scale to choose if you were looking at overarching ideas of trade or perhaps movement. It is absolutely no use using data like this if you wanted to hone in on an individual town, village or site. This is purely for the overarching level of looking at perhaps parts of a country. Nevertheless, if you take an image like this, you can see we're going to concentrate on Avebury. It's going to be around about here, but you can see that, for instance, we've got the Isle of Wight here, so very distinctive. We know where we are in the country. We've got northern France. We've got immediately we've got a relationship shown by this satellite image using this sort of what we call a macro scale. When we move on to slightly more detailed look at sites using satellite imagery, we find that various types of satellite imagery are available, and here are some examples. Now you'll see that each one has a resolution, and that resolution is expressed in meters. That is meters per pixel. So for every pixel on that digital image, it represents 10 meters on the ground. So the more meters there are per pixel, the worse the resolution. The less meters there are per pixel, the better the resolution. So at top left we can see here we've got a Landsat 7 satellite image. This is available freely from the US Geological Service, and that has a resolution of 8.5 meters per pixel, and it's panchromatic, i.e. it's black and white. You'll find that with a lot of these images, when they are panchromatic, the resolution is better than when they are full colour images. The site you can see in the middle, this is the huge earthwork around Avebury, and you can see that at 28.5 meters per pixel, the level of detail is not particularly good. It will be okay for showing some survey work of on a large scale around the site, but picking out individual details is much more difficult. The same image from Landsat 7 here is taken, but it's been pan-sharpened, and when it's pan-sharpened it increases the resolution to 14.25 meters. Now if you look at that and you look at that one, you see that 14.25 is exactly half of 28.5. This data isn't collected at a higher resolution, but it is processed in such a way that it has a higher resolution. And as you can see from the image, it's multispectral. So when you look at the detail in this area here of the earthwork around Avebury, and you look at the level of detail here, you can see that the earthwork here is much more clearly defined. This is a small image. If you were to blow it up, it'd be even better defined. So Landsat 7. Landsat 7 has been going for quite a long time, and it is regularly takes regular data shots around the Earth. But if you want a slightly better resolution, and you can obtain this well, the historic data you can obtain from the US Geological Service again. This has a resolution of 10 meters per pixel. And when we look at the spot satellite here, which is panchromatic, you can see that the field boundaries are much, much clearer. We can actually start to see detail within the satellite image. And you can see here, you can see buildings and so on. So there are three images which are satellite data. My little note here that says corona digitized from film, if you were to go on the US Geological site, you would find that you might be able to get hold of some corona images. These were images taken in the 60s and 70s where they were actually taken as on film, and then the film was ejected from the satellite and caught by a plane with a net on the front, and then brought back down to Earth for scanning and processing. These can be quite high resolution. Most of the examples, however, that I found for Avebury are covered in cloud, one of the problems of living in Britain. To give you some idea of the resolution, though, of satellite images, I've compared them with this, which is an aerial photograph, which is 25 centimeters per pixel. So massively higher resolution than any of these other images. This is obtained from Digimap, which you all have access to, and you can download these and they're all georeferenced, and these are vertical images, so they are spatially correct, but you can see that the level of detail available on this particular image is so much greater than it is on these other ones. This is perfectly suitable for doing some detailed survey work. If you want to obtain any of that image, those images, then they are freely available through Earth Explorer at the US Geological Service. This link does work, so if you're looking at this PowerPoint and you click on this link, it will take you to them. You will have to register, which is absolutely free, and that will allow you to download some of the data on the website. Some of the data on the USGS site is locked, so you have to actually order it and have permission, and some of it is tied into NASA, and if you want to use any of the NASA data, we'll see some shortly, then you need to separately register with the NASA site. If you were to put in, well, if you go from Earth Explorer site here, you'll be able to find the address you need for the NASA site, and then you just simply need to register. If you register with your university address, then you'll have no problem at all obtaining data. Okay. Other satellite imaging that's available with a resolution of 10 meters per pixel is Sentinel satellite imaging. The reason I've chosen this particular one is that at the moment on Digimap, this is all available for you as a resource. At the moment, this resource lasts until sometime in December, and then at that point it's whether the university decides to subscribe to the service. If they don't, that data is still available via the European Space Agency site. The advantage of using Sentinel-2 data is it has a resolution of 10 meters per pixel. So if you're doing a landscape survey, for instance, that's very, very useful scale. But it's also multispectral. So what we're looking at here, for instance, on the left we have a stacked true colour image at 10 meter resolution, which is a conventional colour image, and we see Avebury in the middle here. And on the right we have a stacked near infrared image, also at 10 meter resolution. If you're looking for changes in landscape, perhaps archaeological features, using near infrared can actually be quite useful. If you look at the table at the bottom, these are the other bands that are collected by the Sentinel-2 satellites, and you'll see that not only is there near infrared, there's also shortwave infrared. A lot of these are designed for looking at or monitoring metrology rather than looking for archaeology, for instance, on a land site. But you see here on the left, we've got some vegetation bands within the satellite, and these can be quite useful if you're thinking about differences in vegetation cover representing differences in land use. But in general, when you're using these, you probably want to use the stacked images, which is just basically the red, green, blue all pressed together into an image that you recognise, and maybe the near infrared images. But again, they're very, very useful if you're doing a relatively large landscape survey. If you're thinking about honing down into a very small part of the site, then these aren't particularly useful. The one satellite resource that we all have access to, and it's completely free, is Google Earth. And the current Google Earth satellite images are of a very high resolution. They're higher than the Sentinel 2 that we've just looked at. This is a Google Earth satellite image of Avebury from 2019. Increasingly, we're having more and more Google flights, or they're capturing more data, so the data is being updated more often. So for Avebury, the resolution and the detail from Google Earth is perfectly fine for doing even a detailed survey of the site. So here, for instance, you can see all the standing stones quite happily on here. Obviously, this you would zoom in a much more with this if you actually had the original data. And the colours that we get on Google Earth are really well colour balanced, so it's really quite a useful thing to use for archaeological sites. If you're using Google Earth, you can use a colour image like this, or you can, by taking it into a program, perhaps ArcGIS, you could do this in Photoshop as well, you can make it into a monochrome image. Why would you want to do that? Well, sometimes it's easier to spot differences between objects in the landscape when it's in black and white without the distraction of colour than it is with a full colour image. You can do either of these. So, for instance, here, when we look at the monochrome image of Avebury here, and we say we wanted to describe or transcribe the earthworks, you'd probably find it was much easier to do in black and white than it was to do in colour. So this is monochrome. But you have the choice of doing either. If you download the colour image, you can obviously generate the monochrome image. So that's satellite imagery. A bit of a swift overview of it, but if you're thinking about doing a large-scale survey, then think about having a look at some of the satellite images. There's plenty out there. The next technique we're going to look at is LiDAR, light detection and ranging. There are other versions of what LiDAR actually means, but let's stick with that one for the sake of this lecture. LiDAR, or 3D laser scanning, was first conceived in the 1960s, and it was designed to detect submarines from aircraft. So if you imagine a laser going through water and being able to detect objects within the water, they'd be looking for submarines. In order for a LiDAR system, an airborne LiDAR system to work, you need the LiDAR sensor itself, but you also need a GPS receiver and an inertial measurement unit, which are hooked up to an onboard computer, and then you need a device to store the data. The GPS and the inertial measurement unit are absolutely crucial to locate exactly where the aircraft is, because they need to compensate for differences in the movement of the aircraft. The inertial management unit manages the position of the aircraft in 3 dimensions, and it corrects for the horizontal and vertical movement. Ground GPS stations, as well as the GPS receiver on the plane itself, give a very accurate fix as to exactly where the aircraft is. Once the data is collected, then there are 2 ways of looking at the data. One is to look at a digital surface model. This is the unprocessed data with all the buildings, trees, etc. still in place. Very often for archaeological purposes we want a DTM, which is a digital terrain model, which is the same image but with the trees, buildings and ground cover removed. You have to be careful when you're looking at data that has had the trees and the buildings and ground cover removed, because quite often it's done automatically. We'll cover the problems with that a little bit further on. So this next slide is a very short animation, and it shows the process of data capture. So you can see a light aircraft going along, and the important thing about this is that when you're looking at that image, you can see that the aircraft isn't collecting in a very, very narrow band. It's collecting in a big swathe here as the sensor moves from side to side. The greater the distance between this point and this point here, the less the resolution of the data. The closer the aircraft is to the ground, the better the resolution of the data as well, because if you can imagine that as a laser emits from this sensor here onto the ground, the further away it is, the more spread it will be by the time it hits the ground. So that's why you end up with surveys that are of different resolutions. This is typical of a commercial sensor in an aircraft. This actually belongs to the US Geological Service, this particular one, so it's a very sort of large and robust instrument. But you can see that it's actually mounted so that it's shock proof, so that you get the minimal amount of vibration within the aircraft. This is still the conventional way of collecting LiDAR data. Okay. If you want to obtain LiDAR data, the easiest way to do it is to go to the Digimap website and choose LiDAR on here. If it asks you to register for that particular data set, then just simply fill in the form that it gives you and you get access to it. And here it allows you to download the LiDAR data for using a GIS or in CAD. The coverage is variable, and what we need to do is think about the scale of the project that we're about to do and then decide what is suitable. So here we have different resolutions of terrain data, DTM, and surface data, DSM. So if you're very lucky, you can get hold of half-meter resolution LiDAR data from the Environment Agency. So here we have two examples here. On the left is the DTM, on the right is the DSM. And that gives you the best resolution. At the top here we have 2-meter resolution, so it's the same area, but it's captured with each measurement being 2 meters apart as opposed to half a meter apart. And therefore we have a quarter of as much data. Sorry, a quarter of an eighth or 16th as much data. If it's 1 meter resolution, we have a quarter of as much data. So it's exponential when you go from half meter to 2 meter. Why would you want to have 2 meter data when you can quite happily have half meter data if it exists? Well, the good reason is LiDAR data is very large. And if you collect 2 meter LiDAR data for a large survey that is good enough, you'll find that it's much easier to deal with. Whereas half meter data has got 16 times as much data. So if you're looking at a large area, you're going to find that you're dealing with a much bigger data set. If we look at a couple of close-ups here for a DTM and a DSM for Avebury, we can see that on the left is the DTM. This has been treated with the automatic algorithm that strips out buildings, trees, etc. On the right we've got the DSM, the surface model, which still retains the buildings and in this case the standing stones. And you'll see that on the left, because they've stripped out everything that's above a certain height above ground, they've actually removed all the standing stones. So one of the reasons I chose this as an example is because it shows that in order to process this data properly for a DTM, you need to do it by hand rather than rely on an automated algorithm that's actually removed part of the archaeological data. You can also take images using UAVs. So the images that are captured from the UAV, which are either photographic or video images, can be used to create a digital surface model. They are much more difficult to create a terrain model because, unlike a LiDAR, where it's a physical laser that's pointing at the ground, this relies on a photographic method, and you're always estimating how tall the tree cover is. But it can be used to make a model. This is some UAV footage from a drone over Avebury, and you'll see that the much lower altitude available with a drone enables you to see more detail than you would from a light aircraft. There are restrictions to using drones for commercial purposes, and technically to do this and to collect the data you'd need a CAA drone license. The person who collected this, I suspect, didn't have, because you can see that they're driving over tops of roads, which is actually not allowed. But let's have a look and see what the difference is when we have a look at this drone data. The maximum height you're allowed to be at using a drone survey is 400 feet. So we're going to be well below that, and you can see with this drone data that we've got lots and lots of detail. I mean, you can quite happily see all the cars moving about, all the cars are parked. If this drone were to fly legally at a much lower level, it would also be possible to create a very, very detailed DSM. We have in the department a LiDAR pod that actually fits under a drone, and that allows a collection of data at about 5 centimetre intervals. We'll see a bit of that later when we look at the example from Corbridge. As you can see, this is only a few minutes of footage, but it has covered an awfully large area at quite a high level of detail. This actual footage is slightly longer, but I've taken off the end because it actually follows the road out of Avebury along the line of stones, which you could just about see in the cornfield on the top right there, and as they move out of Avebury. So that's an overview of the techniques of satellite imagery, UAV, and a bit on aerial photography as well, and giving you an idea of scales of data. What I'd like to do for the second part is to take an example, which is from Corbridge in Northumberland, around the Roman town, and look at how you combine remote sensing data together to give you an overall picture of a site. You'll see as we progress through the types of data for Corbridge that in the real world everything isn't quite as rosy as it should be when it comes to things like LiDAR data. So you think you've got LiDAR coverage for the whole of your area, and lo and behold, when you download it, you find that you've got LiDAR data with a big hole in it. So here we have LiDAR data for a digital surface model from Corbridge, and you can see this blue bit here. This is the Ordnance Survey map, that's the time, but you can see there's a big hole in the data. These are 1 metre DSM tiles. As I said earlier, ½ metre is difficult to obtain for a lot of areas, but you'll also see here I've combined these in GIS into a mosaic, and you can see the size of each of the individual tiles here represented by the green lines. On the right hand side we have the same raw data, just with the lines removed, and you can see the detail within it, but this is raw data. This hasn't had any hillshade or anything applied to it. So it's literally a series of points across the landscape at 1 metre intervals, which have then been turned into a series of grayscales to create this raw data image. You can take that data though, and you can, using a computer, GIS is particularly useful for this, and you can take that data and you can apply what we call a hillshade to it, and this gives you a 3-dimensional image. The data is 3-dimensional, but what we're looking at here is some very, very clever lighting based on the slope of the data to create what we call the hillshade so that it looks 3-dimensional. With the DSM, here's a sort of slightly blown up version on the right hand side at 1 to 5,000. You can see that we can see individual properties. The Roman site is here, and this is what I said about data is not always perfect. You'll see that the data that we were collecting actually chops the Roman site in half. This area here is possibly the remains of the enclosure around the Roman town, and then we get this big drop off the slope here to this flatter area at the bottom, which is near the Tyne, and when we have very large tidal surges, this floods, so it's possible we might be looking at the site of a Roman port. The advantage with the DSM data is it leaves all the buildings in place. So if we then look at the next image, which is the same image, but here I've simply blown it up, so it's an outer scale of 1 to 1250, you'll see that you've got a great deal of detail here. So we can see the buildings, we can see all the plough lines in here, we can see the earthworks very, very clearly here. If you were to go to this site and walk along the slope here, you would see that it is like this. It's very rough and very uneven. And you can see here, these are the remains of the Roman buildings here. They haven't been stripped out because it's a surface model, so we can quite clearly see the lines of all the extant Roman walls. This, of course, is the modern town of Corbridge. I say modern, it's probably medieval onwards, but it does allow us to precisely see where the buildings are in relation to the Roman site that we're looking at. We've got the same data here, but this is the digital terrain model. So this has been statistically treated to remove things like trees, houses, upstanding remains to give the ground surface. So what you're interested in with a DTM is the ground surface. That's why it's called terrain model. Same principle as before. We've imported this whole series of tiles from Digimap into a GIS. And this is used to create the model. And again, it's the same data, so we've still got the same big hole. If we then look at the hillshade derived from the DTM, you can see that we've got a great deal of detail showed here, but we've had all the buildings stripped out. So you can see all this area here, all these areas here. This is where all the houses have been stripped out using the algorithm. So you get this rather muddled set of data because that's where they've taken the houses out. It doesn't affect the terrain around the Roman site itself. In fact, it improves it. You can see here that you've got nice earthwork showing up there. But if we were to zoom in, so this is 1 to 5,000, if we were to zoom into 1 to 1250, you can see that we've got a really nice view of the earthworks here. We can still see the ploughing, but this is where all the buildings have been taken out, and you can see all these triangles here where it's tried to create a model from the points that were left after the algorithm had stripped out the buildings. So it's not so good. On here, it's a lot less useful, for instance, for looking at the Roman town. What it is good for is looking at the earthworks around the Roman town, and these are the ones where we actually undertook geophysics, which we'll look at shortly, and you'll see how understanding the topography around the town is very important for understanding the geophysics. You can also collect high-resolution LiDAR data using a drone. And this, believe it or not, I know it looks like a photograph, but this is actually high-resolution LiDAR point cloud data collected by Leslie Davison, who's one of our PhD students, jointly with civil engineering. And she's used a hectocopter, a big hectocopter, with a LiDAR pod on the bottom, and done a whole series of flights across the areas around Corbridge. And she's flown not only in one direction, but also cross-flown. So the resolution of her LiDAR data is something around about 5 centimeters. She's more interested in erosion as part of a PhD, and this sort of level of detail enables very, very precise measurement of changes to the landscape. What you can also see here, this black line that runs across the field, you're looking at it and you're thinking, I wonder what that is. If you were to zoom right in, you'd find that that is a telegraph wire. So the level of detail of this LiDAR data is such that it will pick up something as fine as a telegraph wire or telephone wire. Shows my age. The other data you could use for Corbridge are aerial photographs. So we didn't cover aerial photographs that much in the overview, but here they are very much an important part of trying to understand the landscape around Corbridge. So this is an oblique photograph that was taken in the summer when the weather was very, very dry. And you can see here, this line here, this one here, these are the Roman roads leading from the Roman town, which is here. This is the museum and the car park. And you can also see here in the sort of right-hand side of this field, these parallel lines, and they represent a track that runs across the corner of the field, and that actually might not be Roman, that might actually be part of a medieval system. And then at the bottom of the field here, you can just about see some of these right angles, and these are the remains of some of the Roman buildings that are surviving. Obviously, the value of this photograph in terms of being able to see archaeological features is really good. However, at the moment, we can't actually map any of these features properly until the photograph is rectified. So this is what we call an oblique photograph. It's taken at a strange angle. By using points within the landscape that match points on the photograph, we're able to rectify this photograph. And this is my rectification of it in ArcGIS. And that then enables us to take the data that we've got on this aerial photograph and place it on a map and compare it with the other techniques that we're using for recording the site. I'm sure Karen's probably told you this anyhow in her lecture on aerial photographs. If you want to get any aerial photographs that are vertical, then you can go to Digimap and go to the aerial bit and obtain photographs. The photographs are largely within the past 20 years. but they are all verticals, as you'll see in the next image, and they are georeferenced, so you can literally download them and they give you a picture of a site that is readily available in a GIS. So they only need to be georeferenced if you have a photograph. For instance, the last photograph wasn't from the Digimap resource, so it had to be georeferenced and put into the right place. But when you've got something like Corbridge with lots of buildings around it, it's not too difficult to georeference the photograph. The other thing you can do with the photograph, this is the area here around the Roman town, which we're interested in because we've done quite a lot of geophysics in here. And you can see vaguely from the original photographs a few lines emanating out from the bottom of the Roman town, which is right in this area here. You can take that photograph and manipulate it in either ArcGIS, you can stick it in Photoshop if you want to, and by altering the spectrum within the photograph, it enables you to bring out features that you couldn't previously see. So you can see here all these lighter lines that we can see within the photograph, and the lines here. These are all the remains of parts of Roman buildings. And the reason we can be sure of this is because they exist within other sources. So taking the original image and manipulating the data means that you can make less obvious features more visible. You can also obtain oblique aerial photographs from UAVs. There have been quite a number of these done over Corbridge. This is an example of an oblique photograph taken from UAV. Unlike the aerial photographs, it's taken from a much lower altitude. The lower the altitude, the higher the resolution of the image. So it would enable us to utilize those to create a surface model. And if we move on to the next slide, we can see here that using structure from motion and a whole series of photographs with a UAV, we end up with a three-dimensional model of Corbridge Roman town. This was done using 48 photographs. I didn't do it, somebody else did, and it probably needed quite a few more photographs to obtain a really good model. This is done in a program called, well, it's Photoscale in this case, but it's now Metashape, that allows you to take photographs from a whole series of angles and create a three-dimensional model from those photographs. What you're still left with, though, is the equivalent of the DSM, which is the surface model that we had for Avebury and also obviously for Corbridge, and we're still left with all the trees and the buildings in it. It's very, very difficult to strip those out if you don't have the LiDAR data, because LiDAR can actually penetrate trees and give you some idea of the ground surface, whereas when you're using structure from motion, you're using photographs which don't have any depth to them. You can take the aerial photographs and the UAV data and you can create a transcript from the aerial photographs, and this is a crop mark transcript for Corbridge. And what's happened here is it's taken a whole series of vertical and oblique photographs, and each photograph has been transcribed. So all the stuff in black are the records from the Edwardian excavations, which we'll see in a minute. And all the data that's in this orangey colour, this is data that's been derived from aerial photographs, or from crop marks, or from parch marks. If we can draw all this data into a GIS together so that we end up with the Edwardian plans here and the crop marks, we can then end up with a composite picture of the data. So if we move on to here, we can see the full version of the Edwardian excavations. These are done in about 1910, I think it is, yeah, 1910 onwards. when the lot was excavated. And you can see there's a whole range of buildings outside of the present site that you're able to visit. So all those buildings that were shown up on that aerial photograph where we'd adjusted the spectrum on it are all the buildings within here. But we can still see that there are other buildings here that don't appear on the excavations, so that obviously this is the limit of their excavations. But by combining the two, it enables us to create an overall picture of the extent of the Roman town. However, this is only part of the picture. So the final thing that we would add to this is to do some geophysics. So at the moment, everything we've done has been the traditional airborne or spaceborne remote sensing. The final bit we're going to add in is the ground-based remote sensing, and that is the geophysics that has been done all around the Roman town and has covered a much greater area than has ever been transcribed from the aerial photographs. So let's have a look at this. This is the gradiometry data from the survey around the Roman town. The Roman town is here, but you can see we've covered a much greater area. Within this data, we can identify all the roads which are here, but we can also see that around here and around here we have the remains of all the buildings and plots of land that are on either side of the road coming out from the western side of Corbridge town, and then to the north again we've got a whole series of plots of land along the edge of the road. The big earthworks we can see down here all around the Roman town. This thing here, that big white line, is actually a sewage pipe, one of the hazards of using a magnetic technique. And as we move further to the west away from the Roman town, we can see that we've got a big rectangular enclosure there. We've got some other earthworks here that look like they may well be Iron Age rather than Roman. And then as we move further and further to the west, you'll see that the level of detail slowly disappears and we end up beyond the limit of the Roman town. Same is true to the north here. This field with the big white line across it, which is also a massive sewage pipe, this just had ridge and furrow in it, and there's a big earthwork in it, and there's no evidence here at all of Roman activity. But we can take this data and compare it with the aerial photograph data, satellite data, UAV data, and create a more composite interpretation of a site. Not only do we do lots and lots of gradiometer survey here, we also have, and my final slide, we also have some work done with resistivity, which is an electrical method. So we're passing a current through the ground. If we've got walls in there, we're going to get a high reading. If we've got ditches and pits, we're going to get a low reading. And we can use that to map the data below the current English heritage site. So as you see, as we move south of the Roman town here, you can see in here all the buildings represented within the resistivity data. Why haven't we done such a big area as we have with the gradiometer? It's because this takes about 10 times as long as very slow. So I hope from that you can see that by taking lots of different remote data and merging it together, we can end up with an overall picture of a site. If you want to follow up on any of this, then your best avenue is to look at some of the data from Digimap. And obviously, if you are so inclined, if you want to try and amalgamate this in a GIS, you'll find that it's probably one of the easiest ways to manipulate the data. So I think that's it. Thank you and goodbye. 50 minutes. That's enough. Oh no.